This is question 38 from the GATE 2021 EE paper, in which we are given nilpotent matrix A, that is a matrix A such that A power 5 is a null matrix, and we are asked to find the determinant of A plus I. Underneath the question, you will find the title of the NPTEL course or video relevant to this topic. So in this question, we are given a matrix A, which is a 10 cross 10 matrix, such that A power 5 is equal to 0. That is, A power 5 is a null matrix. Such a matrix is called a nilpotent matrix. Right? If there exists a natural number such that raising the matrix to that power yields the null matrix, then the matrix is called nilpotent. In this case, for n equal to 5, we yield the null matrix. In this question, we are asked to find what the determinant of A plus I is. Now, one thing you need to know about nilpotent matrices is that if lambda is an eigenvalue of A, then it must be the case that lambda is equal to 0 for when A is nilpotent. Right? And the reason for this is that A can be broken down into the following Jordan form: Tj T inverse, where J is equal to lambda 1, lambda 2, so on till lambda n, where these are the, or in this case, since it's a 10 cross 10 matrix, lambda 10, with potentially non-zero entries above it. Right? This is the Jordan decomposition of A. And if you do not require the proof of this fact, this is the proof of this fact that I am doing now, please skip to the point where I start solving the problem. So what will A power 5 be now? It will be Tj T inverse the whole power 5, which is equal to Tj T inverse into Tj T inverse, and so on 5 times. Right? Now T into T inverse is I, so that disappears. So every T inverse and T in between two J's will disappear. So this will be T J 5 times and then T inverse. Right? So this is T J power 5 T inverse. But this is equal to 0. And since these both are invertible, I can just pre and post multiply by them, by their inverses. And we get J power 5. Now these both are the identity matrix and I can ignore them. So we get J power 5 is equal to 0. Now looking at this, you can see that if J is like that, then what will J power 5 be? If you work it out, and I'm only interested in the diagonal entries of J power 5. What will be the diagonal entries of J power 5? If you work it out, J power 5 will have the diagonal entries lambda 1 power 5, lambda 2 power 5, so on till lambda 10 power 5. It will have some non-diagonal entries, of course, but the diagonal entries will be the following. Now since this is equal to 0, we can clearly say that all the eigenvalues raised to the power of 5 must be 0, which must mean that all the eigenvalues, like for example, if lambda 1 power 5 is equal to 0, it must be that lambda 1 is equal to 0. So like this we get that for all I, lambda I is equal to 0. Right? So this is the proof that of the following statement: if A is nilpotent and if lambda is an eigenvalue of A, it must be the case that lambda is equal to 0. Now we'll use this fact to solve this problem. Right? All eigenvalues must be 0. Now let's say X is an eigenvector of A plus I with the following eigenvalue lambda. This is basically that A plus Ix is equal to lambda x, and I can take this Ix onto the right hand side and get that Ax is equal to lambda minus 1x. Right? That means that x is an eigenvector of A with the eigenvalue lambda minus 1. But all the eigenvalues of A must be 0 by this statement, which means that lambda minus 1 is equal to 0, which means lambda is equal to 1. That is, if x is an eigenvector of A plus I with eigenvalue lambda, it is that lambda has to be 1. That is, A plus I has only lambda equal to 1 as an eigenvalue. So finally, since determinant of A plus I is the product of its eigenvalues, we get that determinant of A will be 1 into 1 into 1 and so on, how many ever eigenvalues A has, how many ever algebraic multiplicity of the eigenvalues are, so which is equal to 1. Thus the correct answer is 1. And again, the reason for why determinant of A plus I is the product of eigenvalues, the idea is that eigenvalues are the roots of the characteristic polynomial lambda of, let's say for a matrix B, a square matrix B, if lambda is an eigenvalue, then it is that B minus lambda I, determinant of the characteristic polynomial B minus lambda I has the roots as the eigenvalue. So now this can be given, since they are the roots, as the product of lambda I minus lambda I equal to 1 to n, where n is the where n is the size of the side length of the square matrix B. Right? Now if you were to make lambda equal to 0 in the above expression, you get that determinant of B is equal to product of I equal to 1 to n lambda I. Right? So therefore these are the roots of the characteristic polynomial, and we get this expression, and so we get that the determinant is equal to the product of the eigenvalues, and so therefore the correct answer is 1. The answer here is 1.